Hey guys, this is Chapter 11, Sections 1 and 2, and we're going to start by talking about pressure. So the amount of pressure you exert depends on the area over which you exert that force. So if you have a smaller area like your tennis shoe trying to walk on snow versus a snowshoe trying to walk on snow, you're applying more pressure with the tennis shoe because you have a smaller area. So let's go back and talk about what area is. You have to calculate it by multiplying. So 2 times 3 here is going to give you 6 centimeters square. So which has a greater area, the rectangle that is 4 by 20 or the square that's 10 by 10? Well, the 4 by 20 is 80 centimeters squared and the 10 by 10 is 100 centimeters squared, so the 10 by 10 is bigger. So you just need to make sure you're able to multiply the length and the width in order to get the area. When we measure force, we always measure them in newtons per meters squared, and 1 newton per meter squared is called a Pascal. All right, a fluid. A fluid is any material that can easily flow and change shape. So we know fluids are both water, liquids, and gases. So all the forces exerted by the individual particles in a fluid combine to make up the pressure. So think about what's going on here in this chair, what's going on inside the chair. Because the person's sitting on it, those particles are hitting each other more often and they're more crunched into a smaller space versus the outside air. So there's more pressure on the inside of the chair pushing out than there is on the outside pushing in. So there's a lot of variations that happen in fluid pressure. So let's think about just atmospheric pressure. Here is sea level here. As you rise up, the atmospheric fluid pressure becomes less. That's why you have to have pressurized cabins in an airplane. Versus when you're here at sea level, you don't have to have any kind of pressurized situation. Now, as you go down from sea level into the ocean or into the sea, it increases in pressure. And that is because now you not only have the atmospheric pressure pushing on you, but you also have the pressure of the surrounding water pushing on you. And that's why there's a limitation to where people can go versus where we can send machines, or even where some fish can survive. And a barometer is used to measure atmospheric pressure. So we're going to talk about density and how a hot air balloon works in just a minute. And density, you got to know that density changes. Our density can cause a submarine to dive, rise, or float. And so this is how a submarine works. We have a tube, which is like the living quarters and everything, all of the machinery, and then inside of it, other tube. And when it's going to dive, it's going to allow water into this tube, and air is going to come out the top. So its density increases, and this submarine dives because its density is greater than the surrounding water. Then when it's just floating in the middle, its density is the same as the water. And then in order to rise up, it has air compressors here. It pushes air out, which then pushes the water out and down. And because this outer tube is replaced with just air, the submarine's density decreases and becomes less than the surrounding water. Now, buoyancy. Buoyant force always works upwards. So remember that we have pressure working in all directions towards this fish, and inside the fish pushing back out. But buoyant force only works in an upward direction. So the buoyant force is what allows things like fish or boats to float. And we're going to talk about the floating and sinking of the Titanic during class. So the buoyant force works opposite of the weight. So remember, the downward gravitational force, that's the weight. Upward force is the buoyant force. So if you have something like a jellyfish where the weight's not very much, the buoyant force is going to allow it to float on the top of the water. Then you have something like a turtle, the weight's pretty decent, and the buoyant upward force working on it, they're going to be equal. So that's how come the turtle can be in the middle, or be in neutral buoyancy. And then the downward pull of gravity or weight on this lobster is going to overcome the buoyant force. That's why it's crawling on the ground. So buoyant force, which is Archimedes' principle here, it states that the buoyant force acting on a submerged object, so something that's underneath the water, is equal to the weight. So let's look at this. This is completely sunk. Well, maybe it's filled with rocks. I don't know. and we catch all the water that comes out. This is the displaced fluid. If we find the weight of this, then that's going to tell you how much the buoyant force is working on the canister. And when it's only partially full with something, so only part of it is submerged and the rest isn't, it's only going to push out water that's equal to the submerged part of the canister. So if we find the weight of that displaced fluid, then we're going to know that the buoyant force, what the buoyant force is working on this item. So when you think about a block of wood and or block of steel, if it's just in a solid block, it always sinks because the weight's so great and the buoyant force working upward on it, it's not able to displace very much water, so the buoyant force is not very much. But if you take that same block of steel and you hammer it out to a nice flat shape, then yes, the downward weight might be the same, but the buoyant force, because it's displacing all this water that it's taking up here because the volume has increased, it's displacing all of that, and then the buoyant force working upward on that same piece of metal that now has been made into the bottom of a ship is actually greater. And that's it.